our last video for the semester. So in this week E material, I'm going to go over week E and week F. We're going to talk about independence and dependence. So just to define those terms, linearly independence means there are separate vectors, separate information. If they're dependent vectors, then that means they have the same information. Means they're not all independent, they're not all separate. Okay, so the reason why we care about that is because when we have a system of equations, we have multiple different kinds of options. We have multiple options. If you think about it graphically, these are our three options graphically. They're either two separate lines where their intersection point is the solution, or they're the same line where they have an infinite number of intersection points. So here's one solution, here's an infinite number of solutions, or we have parallel lines where they never overlap. These are no solution. So these two vectors, or these two lines, are two separate lines. They are independent lines. These two vectors are dependent. It's the same information. And these two vectors have conflicting information. If we think about our system in terms of vectors, so let's say I have a vector system, so writing it as a linear combination, where I have an x vector, a y vector, and my b vector. This is what it looks like comparatively. My x and y vectors are separate, and b is also separate. This same idea happens, we have one solution. If all three of those vectors are collinear, they are on the same line, then we have an infinite number of solutions. And if my x and y vectors are on the same line, but my b vector is not on the same line, here's where I have no solution. So here are my three options. And it turns out there's terms for these types of systems. So if we have one solution or an infinite number of solutions, our system is considered consistent. Options being one solution or infinite. And if we have no solution, my system is inconsistent. Okay, so if my vectors of A, if these x and y vectors are non-parallel, non-collinear, the system is consistent and has one solution. So I have this scenario here. If the vectors of A are parallel and collinear, so my vectors of A are parallel and collinear, they're also parallel and collinear with my B vector. So notice here I have all three of them on the same line. Then my system is consistent with an infinite number of solutions. And if my vectors are parallel but not parallel with B, or my lines are parallel and don't intersect, then I have an inconsistent system with no solution. So there's a couple different ways that we can figure out whether or not we have a consistent system or an inconsistent system. If we have one solution, infinite number of solutions, or no solution. The first one is setting up our vectors as a linear combination. So our vectors are said to be linearly dependent on another if one of them is a constant multiple of the other. So if we want to figure out if they're constant multiples of the other, we write it out as a linear combination. So C1 V1 plus C2 V2 plus C2 C3 V3, etc. Set that equal to 0 and solve for our constants. Solve for C1, C2, C3. If our constants are all 0, then that means 0 equals 0. We multiply all of our vectors by 0, it equals 0. That is called the trivial solution. You already know that. 0 plus 0 plus 0 equals 0. If all of our constants or some of our constants are non-zero, then we have a linear combination. So something like this, 3v1 plus 2v2 plus 7v3 equals 0. If we have a scenario like this where some of our constants are non-zero, then they are linear combinations of each other. So here's how we set up linear independence problems. Method 1. Set up our vectors as linear combination. C1, V1 plus C2, V2, etc. equals 0. Solve for our constants. If our constants are 0, our vectors are independent. They are three separate pieces of information, or 4 or 5, however many vectors we have. If some of the constants are non-zero, the vectors are linearly dependent, which means some of my vectors are multiples of other vectors. They repeat the same information. Then we have this theorem here. You can call this method 2, method 1.5. which tells us that if we have n vectors in Rm. So here's n is my number of vectors. In Rm, the space they live in. If n is greater than m, then the set of vectors is linearly dependent. So this is just easy to say. So if we have 3 vectors in R2, 3 is greater than 2, therefore they're automatically linearly dependent. Because we can always say that 3v1 plus 4v2 equals v3. And we can always solve for some constants to get to this other vector that exists somewhere, as long as they're in the number of vectors is greater than the space they live in. Okay, that's method 1.5. Method 2 is using what's called the rank of a matrix. So the rank of a matrix is the maximum number of linearly independent rows or columns in a vector. It doesn't matter if they're rows, doesn't matter if they're columns. Same thing, same answer both ways. To find the rank of a matrix, we go ahead and put our vectors inside of our matrix and reduce it to REF, do our Gauss elimination. The number of non-zero rows after REF is found is the number of linearly independent vectors in the matrix. So if we want to find how many vectors are linearly independent, we put all of them in a matrix. Rows or columns, doesn't matter. Use our row operations to reduce it to REF, and then figure out how many non-zero rows we have. If the rank equals the number of rows, so if rank of A equals the number of rows, then the vectors are linearly independent. All of them are linearly independent. But if the rank is less than the number of rows, if I have non-zero rows, or if I have 0 rows exist, then my vectors are linearly dependent. It means that some of them are linear combinations of others. And generally where we apply this, or where we can apply this, is in Gauss elimination. So if you remember, we had 3 options for Gauss elimination. We ended up with an REF that looks like this. Or we ended up with an REF that looks like this. Or I ended up with an REF that looks like this. Essentially what we're doing when we do Gauss elimination is finding the rank of our matrix, where this side over here is the rank of A. And then if we look at all of it, it's the rank of AB. Where the rank of A checks to see if the left-hand side of our equations are independent, and rank of everything, rank of AB, checks to see if our entire equations are independent, because it depends on what B looks like. If we go back up to our graph here, it depends on what B looks like. If our B vector is on the same line as our X and Y vectors, we have infinite solutions. But if our B vector is not on that same line, then it's no solution. So it depends on what B looks like. Okay, so here's my 3 options. If the rank of A equals the rank of AB, that's what I have here. The rank of A equals rank of AB. The rank of A over here is 3, and if I follow it all the way across, it's also 3. If I have that scenario, then I have a consistent system with one solution. I have a unique solution. I get one answer. If the rank of A over here is less than the rank and the number of rows, so here my rank of A would be 2. Rank of AB follows as well as 2. If I follow it all the way across, the zeros go all the way across. Then I have this scenario here. I have a consistent system and infinite solutions. And we already know that, but now we're formalizing that, that theory, that context. The last option here, if I look at just A, rank of just this is 2. I have a 0 row. But if I look at the rank of AB, if I go all the way across, the rank of AB is 3. If the rank of A does not match the rank of AB, then I have an inconsistent system and I have no solution. This is why Gauss elimination and Gauss-Jordan elimination can be really useful, is because it automatically tells us right away what kind of system we have and how many solutions we have. Last method is using the determinant. So remember when we talked about Cramer's rule, and I mentioned that to use Cramer's rule, our inverse has to exist. That's essentially what this is aimed at. If A is a square matrix, then the column vectors of A are linearly independent if and only if our determinant is not equal to 0. Which means that if the inverse exists, our vectors are linearly independent. If the determinant A is not equal to 0, then our vectors are linearly independent. If A equals 0, then our vectors are linearly dependent. So, here's a summary. Here's a summary of everything we can conclude given one piece of information. For an A matrix, if my vectors are linearly independent, if my vectors in A, if my rows, if my columns, doesn't matter, if they are linearly independent, that automatically means that the determinant of A is not 0, that it's non-singular, that A inverse exists. It means that I'm going to have a unique solution. I'm going to have one solution for every single B vector. It does not matter what B looks like. I will have a unique solution. It also means that the rank of A equals the rank of AB equals n, which is the number of equations I have. And if B is 0, AX equals 0. This is called a homogeneous system. So if B is 0, then my solution is only going to be the trivial solution, is only going to be X equals 0. Which seems weird, but it's true. Second set of systems, second set of statements. If my vectors of A are linearly dependent, automatically that means my determinant equals 0, A is singular, and then depending on whether or not what B looks like, because remember, up here, depends on what B looks like, whether or not B is in the same line as X and Y, or if it's not, then I can either have a consistent system with infinite solutions, so here's option 1, or an inconsistent system with no solution. It depends on what rank looks like. If the rank of A equals the rank of AB, then it will be consistent infinite solutions. If the rank of A is not equal to the rank of AB, then it's an inconsistent system with no solution. And if I have the homogeneous system, so once again AX equals 0, then automatically it's going to be consistent with infinite solutions. And this information is summarized in this graphical thing down here. So over here I have my homogeneous system, where it's always consistent. If I have a determinant of A is not equal to 0, then my solution is going to be X equals 0. If the determinant of A is equal to 0, then it's going to be infinite number solutions. Over here's my normal system. To determine whether or not it's consistent or inconsistent, I can check to see what my rank is. If the ranks are the same and my determinant equals 0, then I'm going to have an infinite solutions. If my rank is the same and my determinant of A is not equal to 0, then I have a unique solution. And if my rank is not the same, if they don't match, then it's an inconsistent system and no solution. That is weak E material, and we'll go over examples and talk about how to infer information, how to define dependent, linear to independent, all that fun stuff. Okay, on to week F, last set of material. The last set of material is talking about eigenvalues and eigenvectors and diagonalization. It seems a little bit different from what we've been talking about before, but there's applications for it, but we're going to go over the general ideas. So, turns out, when we multiply a vector by a matrix, when I do this matrix multiplication, I'm going to get 2 plus 2 equals 4, and 6 plus 4, 10. Essentially, what I'm doing is I'm moving my vector in space. I'm taking this 2, 1 vector, and I'm moving it to a different location, moving it up to 4, 10. It starts here, and I'm just transposing it. Not transposing, that's the wrong word to use. I am moving it in space to a different location. That's what I'm doing when I'm doing matrix multiplication. moving my vector from one location in space to another location in space. Turns out there are some vectors, when we do this matrix multiplication, my vector is just extended along the same line. So rather than moving it from like here to like over here in space, that's not a straight line, I'm actually just moving it, like I'm doubling it or dividing it by half. I'm moving it along the same line. That is what an eigenvalue and eigenvectors are talking about. So this is essentially what we're trying to say. I want to figure out which vectors for a matrix this happens. Where ax, when I multiply a times a vector, it's equal to that vector just multiplied by a scalar. This is my scalar. And here's my vector. So I want to figure out what are my scalars and what are my vectors. This is called the eigenvalue problem. Figuring out which vectors this appears for, which vectors this works for each matrix, and what constants are they multiplied by. So here's what we're going to do. In order to figure out for which vectors this happens, we are going to rewrite this system, or these equations. I'm going to go ahead and say ax minus lambda x equals 0. Move this to the other side. I'm going to factor out x. When I factor out x, I need to go ahead and multiply lambda times identity, because lambda is a constant versus a is a matrix. But this becomes my system of equations. I'm essentially trying to see which vectors does this work for. So notice this is a homogeneous system. When I have a homogeneous system, I have one of two scenarios. I either have my determinant of A not equal 0, A inverse exists. When that happens, my only solution is x equals 0. I'm not interested in this one. This one's not interesting. 0 equals 0. I already know that. I'm interested in this one, where the determinant of A equals 0 and I have an infinite number of solutions. So here's what we're going to do. We're going to go ahead, take this matrix here, this resulting matrix here, and force it to have a determinant equal to 0. That's what this is. It's called the characteristic equation. I'm saying the determinant of A minus lambda I equals 0. Notice lambda's unknown. Lambda's unknown. So essentially, I can use this to solve for lambda. Solve for which values this is true. What that's going to do is that's going to give me my eigenvalues. So I have as many eigenvalues as I have rows in a matrix. So if A is a 2 by 2, I have 2 lambdas, lambda 1 and lambda 2. If A is a 3 by 3, I have 3 lambdas, lambda 1, lambda 2, and lambda 3. If I have a 4 by 4, then I have 4 eigenvalues, etc. Some of them repeat. Sometimes lambda 1 is equal to lambda 2, but it's still 3 eigenvalues. Then what I'm going to do is I'm going to go ahead, I'm going to plug them in to this system one at a time. Plug in my lambdas, plug in A minus lambda 1 I x equals 0, solve for x. Note, the determinant of this equals 0. That's what I've done. I've forced it to equal to 0. Which means if I go back up to here, if my determinant equals 0, I have an infinite number of solutions. So what we're going to do, we're going to use Gauss-Jordan elimination, because it's really good when we have an infinite number of solutions. We expect infinite solutions, so we use Gauss-Jordan elimination. When we do that, we end up with something that looks like this. 1, 0. And not always, but something along those lines. This is what we would expect. We expect a zeros to fall out because we have an infinite number of solutions. So we expect something like this, where we have one's along a diagonal. This is a number, this is a number, this is a number, this is a number. Not all, oh, these ones are 0. My bad. These ones are 0. So we end up with something like that. Which means here, let's say this is 3 and this is 2. This would tell me x1 plus 3x3 equals 0. This tells me x2 plus 2x3 equals 0. Or x1 equals negative 3x3. x2 equals negative 2x3. So this gives me an infinite number of solutions. What we're going to do is we're going to pick one of our solutions. So we're going to say x equals one of them. I'm going to choose x3 to be 1. If x3 is 1, that means x2 is negative 2. x2, 1 is negative 3. This is one of my solutions for this scenario. Whatever happened. Solving this, let's say I got to that. And the one we typically choose is usually the smallest whole number vector. But that's going to represent my eigenvector for my given eigenvalue. So if this was the result from lambda 1 equals 3 and x1, essentially I'm saying if I take a times x1, I should end up with 3 times x1. Obviously this would be for a real example, but this is just, in general, an example. Note there are an infinite number of solutions. So in reality, my eigenvectors are all linear combinations of x1, so it's all cx1. So any constant. So that's my family of eigenvectors, is my constant times whatever one of my solutions. So if we want to go ahead and find the eigenvectors and eigenvalues for a matrix, we're going to go ahead, use our characteristic equation to solve for lambda. Then we're going to plug each lambda into this system. A minus lambda 1I times x equals 0, solve for x. We're going to use Gauss-Jordan elimination because we are expecting an infinite number of solutions. And for our solution, we're going to pick one vector, the smallest whole number eigenvector, to represent our family of vectors. Okay, the last thing to talk about is diagonalization. So eigenvectors and eigenvalues can be used to diagonalize or uncouple a linear system. Similar to how we had LU factorization, where we break A up into a product of two different matrices, it's similar ideas. When we're breaking A up, we are essentially trying to find a different way to find information about our system equations. So the A matrix, the A is diagonalizable if and only if it has n linearly independent eigenvectors. And it turns out my eigenvectors are independent when I have distinct eigenvalues. Because when I have distinct eigenvalues, my eigenvectors are all unique. They're all different. If I had repeating eigenvectors, then A minus lambda I x equals 0 looks the same if two of my eigenvalues are the same. But if all of my eigenvalues are different, then I'm going to end up with 3 different unique eigenvectors. So therefore, if I have eigenvalue of 3, if it's a 3 by 3, different eigenvalues. So if I have different eigenvalues, I'm going to end up with different eigenvectors, which means they are linearly independent. The diagonalization, essentially this is what we're looking for. This is our diagonalization. So in order to find our diagonalization, we need to find 4 matrices. We need A. A should be given to us. We also need to find X. X is just a matrix of eigenvectors. So if we have A as a 3 by 3, we're going to find all the eigenvalues. We're going to find all the eigenvectors. And then X is just putting those eigenvectors inside of A as columns. So eigenvector 1, eigenvector 2, eigenvector 3. X inverse is just the inverse of X. So we find the inverse. And then lambda. This here is capital lambda. Capital Greek letter lambda. Lambda is a matrix that looks like identity, but instead of ones along the diagonal, it's going to have our eigenvalues along the diagonal, where the eigenvector for my first column in X, its corresponding eigenvalue is in the 1, 1 location. In column 2, my eigenvector, its corresponding eigenvalue is in the 2, 2 location. My eigenvector for column 3, its corresponding lambda is in the 3, 3 location, etc. And I keep working my way across. So if I want to find the diagonalization for an A matrix, I'm first going to find the eigenvalues of A using my characteristic equation. A minus lambda I, set the determinant equals 0. Then find the corresponding eigenvectors by saying A minus lambda I, x equals 0. Plug in my different lambdas. Then I can go ahead and take those values, plug them into lambda and x, respectively, find the inverse of x, and write my diagonalization. And that is how we do the diagonalization of a matrix. So applications of eigenvalues are extensive. It goes beyond the scope of our course. But here's some information. We can use them to solve systems of differential equations. We can use them to find information about material deformation, dynamic systems, signal image processing, principal component analysis, numerical methods, control systems, pattern recognition. All of these places is where eigenvalues show up. All right, so if we look at our eigenvalues and eigenvectors, in some instances, depending on our system, it tells us a little bit about how our system of equations, how our material deforms. So for example, material deformation. If we find the eigenvalues and eigenvectors of a matrix, it can tell us, okay, it's deforming in this direction and in this direction. My vectors can tell me in which direction it's deforming. My eigenvalues can tell me how much it's deforming by. So it really just depends on our application, how our model of our system is set up. But the eigenvectors and eigenvalues are really important in higher level courses, specifically if you get to graduate school. If not, that's totally fine. Just follow along with how our examples show how to actually perform the math.